Thank you, Dr. Akash. And first of all, I would like to thank Department of Nephrology for giving me this opportunity. Advances in the biopsy technique in glomerular pathology. So, I've tried to cover the advances which have been made, some mainly clinically relevant advances which are made in the field of nephropathology in the last decade or so, and another few which basically have just come up recently and are going to be big in coming future. Another part is that the complement system we have deliberately skipped this talk because it's going to come in the talks after this. So instead of to avoid repetition, actually, I have not put too much focus on the complement system. So we'll start with the overview of the talk. So we're starting with the paraffin immunofluorescence, how it has been used beyond salvage technique in nephropathology in last decade. Laser microdetection (LMD) has been used extensively in last decade, especially in diagnosis of amyloid as well as membranous and detection of various lower antigens for membranous nephropathy. We'll move on then to advances in electron microscopy, and then move on to the gene expression based assays which have been used in transplant pathology like MMDX, and finally we'll end with the status of artificial intelligence in nephropathology. So paraffin immunofluorescence. Paraffin immunofluorescence was earlier used mainly as a salvage technique whenever the frozen tissue was not available to do immunofluorescence. That was the only scenario when paraffin immunofluorescence was used. But in recent decade, in last one decade, there have been many studies which have shown that paraffin immunofluorescence also exposes the masked antigens, masked immunoglobulins or masked antigens, which are actually missed on routine immunofluorescence. This is the study from Dr. Patrick Walker and his group, where actually they have done this both as salvage technique as well as for the purpose of unmasking. So in this particular study, they actually had this study had 304 biopsies which were studied, and out of this 207 were used. They were actually paraffin IF was done for salvage, that was 97 where it was done for unmasking. And when you can see that we concentrated more on this unmasking, and for 61 cases it was done for unmasking of immune complex deposits, whereas immune complex, and in 36 it was done for paraproteinemia. In paraproteinemia cases, majority of the cases, at 34 there was no change in the diagnosis, but there were two cases where there was change in the diagnosis or there was contribution by the paraffin immunofluorescence in the diagnosis. The first case was rather a case of mixed LCDD with light chain tubulopathy. The light chain tubulopathy was actually missed by routine immunofluorescence, and that was picked up by the paraffin immunofluorescence. And similarly, there was second case which had light chain tubulopathy with light chain crystallopathy, where the crystals was not detected by the light chain crystals were not picked up on on routine immunofluorescence. When we looked at the cases where it was done for immune complexes, in almost 2/3 of the cases, the diagnosis remained same. There was no change, but in 20 cases, there was significant change in the diagnosis. And these were the details of the cases, and predominantly these were actually either C3GN or autoimmune GN on paraffin on routine immunofluorescence. But when it was actually paraffin immunofluorescence was done, you can see that many of these C3GN actually turned out to be the membranous like glomerulopathy with monoclonal IgG kappa deposit. Many of them with MPGN, they actually turned out MPGN versus C3GN diagnosis, they actually turned out to be essential mixed cryoglobulinemia. And many few MPGN also turned out to be MPGN with monoclonal IgG. So these were the cases where there was significant change in the diagnosis because of the paraffin immunofluorescence. Of course, it cannot be done in each and every case, but there are specific clinical scenarios and biopsy findings which warrant actually paraffin immunofluorescence. First and foremost being C3GN. In C3GN, one must always do unmasking for immunoglobulins. Only then, on paraffin immunofluorescence, on unmasking also you're not finding any immunoglobulins. That is when you can surely say that this is more likely to be glomerulonephritis. Another part is that when you're seeing discrepancy between light microscopy and immunofluorescence, or discrepancy between immunofluorescence and electron microscopy. Say you have one proliferative feature on LM, but you're not finding too much on immunofluorescence. So this is an indication that you should go for unmasking of the deposits. Similarly, if you're finding deposits on electron microscopy, you're not finding much on immunofluorescence. Again, it's an indication for paraffin immunofluorescence. And another is, of course, paraproteinemia. When you are strongly suspected, the patient is having paraproteinemia, you are strongly suspecting renal involvement by paraproteinemia. There you have the indication of paraffin immunofluorescence. Now, why these deposits? They are not picked up on routine immunofluorescence. This still, there are hypotheses, but this is not clearly proven. What they say is that during formalin fixation, which we do for the tissue for light microscopic examination, these cross linkages which take place in the tissue protein, and these cross linkages really hold these immunoglobulins at their place. And that is why when you do paraffin immunofluorescence from that formalin fixed tissue, these proteins can be detected. But it might just be possible that when for frozen tissue for immunofluorescence, these cross linkages will not take place, and that is why they might just be washed off during the washing step. It takes place in the routine immunofluorescence. And the other hypothesis is that they may be resistant to the antibody binding without antigen retrial. Of course, there are limitations of paraffin immunofluorescence as well, that it has to be interpreted carefully. That there is background screening, so interpretation requires considerable practice as well. Another part is that C3 it actually can be used to exclude C3, but cannot be used to diagnose C3. I mean, C3 it will not sensitive technique for picking up C3. Another part is the linear IgG deposits which we see in anti-GBM disease. These are also one which are not a sensitive technique for picking up the anti-GBM disease. So moving up to the laser microdissection, LMD has been used quite extensively in research in last more than 1 decade actually, and it has been used for the postgraduates who are there in this group. I mean, LMD is a direct tool for isolating the specific cell type or the cell of interest from the sectioned tissue. So what you actually do is you mark out the area of interest in the software and then separate this cells of the interest from the rest of the cells using the focus laser beam, and then these cells are actually taken up, this area of interest is actually taken up by either a laser pulse or by using an adhesive slide. This is just an example, a photograph of amyloid which has been fused with congruent skin, and we can see this glomeruli which have been punched out and used for laser microdissection. So it has been used extensively in the diagnosis of amyloid. But why actually I wanted to put it here was that for amyloid, especially when you think about non-AL and non-AA amyloid, then we actually are many times stuck there after when we have AA stain negative or AL stain, or our immunofluorescence is completely negative. And we know that it's an amyloid, but the typing of the amyloid is actually stuck at that stage. So this is the area where this can pitch in, not just as a research tool, but also as a diagnostic tool for the known amyloid proteins. Of course, it will require certain tweaking, like the tweaking which will include the shorter column time, we will require thinner sections, and this will the advantages which it offers are single test which can identify the amyloid protein in question. As I said, that when you have non-AL and non-AA amyloid, what happens is that then you have to put a battery of immunohistochemistries for this. Renal biopsy being a needle biopsy, sometimes you are actually limited for the amount of tissue for the serial sections for the immunohistochemistry. So there, because you have got a single test which can tell you the protein in question, so there this might just play a role here. So it can be performed directly from the tissue involved. I'm not saying in every case of amyloid it is required, obviously, because when you have straight away AA and AL amyloid, which are the predominant amyloid in our population as well, which we see, so this can be picked up by our routine IHC itself or immunofluorescence. But apart from that, the remaining cases, this could be there. So another part is that it will not require any frozen material, and difficult cases, especially those which are heavy chain amyloid, they can be diagnosed using this. And early amyloid cases where the staining is equivocal, very early stages where the congruent staining is equivocal, there it can play a role. And also in familial and hereditary amyloid. LMD in membranous, a lot of research has happened in last decade membranous, and all these antigens. Initially, as we know, the plateau and thrombospondin was the antigens, and followed by this long explosion of antigens which have been associated with membranous. And most of these have been detected by using this LMD only, LMD and mass spectrometry based proteomics. But here, as not just as a research tool, this can also be used as a diagnostic tool in specific scenarios. There are IHCs which are available for all these markers. Many of these markers. In our center also we do immunohistochemistry for plateau, and if this case turns out to be plateau negative, then we have a panel for plateau negative membranous which we cover NEL1, cinnamomum, exotoxin, and NEL1, cinnamomum, exotoxin, and thrombospondin. So what happens is that if still this panel is also negative, then again you are stuck, and the tissue again in some scenarios may be limited here. I mean, for those serial sectioning and immunohistochemistry. This is why this single test can offer help the protein in question. I mean, the antigen in question. So it can be used as a clinical platform as well in certain clinical scenarios. And the differences will be that it will include thinner sections to conserve the biopsy, quicker spectrometry time, shorter columns, and settings to detect the known antigen. So what are the approaches which can be used? Of course, the first approach will be that you can use it in plateau negative and this secondary panel negative membranous, which actually is the most cost effective in our study. That plateau negative and secondary panel negative, this basically plateau and this panel which usually cover around 80% of the membranous. So what you are left with is only around 15 to 20% of the cases of membranous, which will require actually this mass spectrometry based proteomics. Only plateau negative will still, I mean, around 50 to 60% will be plateau positive. So 40% of the membranous they will require if you follow this approach. And this upfront in all membranous is not feasible in resource constrained setting in our country. It will save time in cases with plateau and secondary panel negative membranous, but it will not be economical in our resource constrained setting like India. So the limitations of that, even in plateau negative membranous nephropathy, there will be 20 to 30% of the cases. Still, the known antigen will not be detected here. It can be missed on this mass spectrometry, etc. And when immune complexes and subepithelial electron dense deposits are included in the testing, the sensitivity will go down still further. Mass spectrometry is also being used in transplant for diagnosis of rejection here. In this particular study, they actually used proteomic biomarkers with machine learning for the diagnosis of T-cell mediated rejection. So what this is actually a pilot study. They've actually taken 5 patients with stable function, 5 patients with T-cell mediated rejection, and 5 patients with BKV nephropathy, histologically proven. And what they have done is they've taken the tissue samples from them. They've actually done the protein digestion, and then they've done the mass spectrometry. And the data which was obtained, they actually went for statistical analysis, and they analyzed that which are the differentially expressed proteins or DEPs in this T-cell mediated rejection group as well as in the BKV nephropathy group as compared to the stable graft function group. These differentially expressed proteins, this database of this differentially expressed proteins, then actually it was used in machine learning model to develop a prediction model for predicting this T-cell mediated rejection. This was just the photograph which shows that this was the various differentially expressed proteins and to which metabolic pathways they belong, and these were the one which were upregulated. The upregulated one usually they belong to the one environmental and information processing and genetic information processing, where the metabolic proteins which are the one which have been downregulated there. So what they identified was there were 329 differentially expressed proteins in this T-cell mediated group as well as 467 DEPs in your BKV group, which were as compared to the stable function. And when this whole data set was then entered in this machine learning algorithm, actually developed the prediction model had accuracy of around 80%. When it was used on a blinded manner on an independent sample surface. It still leaves much to be desired, and it being a small pilot study, obviously such proteomic based studies, assays, they will require much larger and thorough clinical validation with large multi-center trials. But once such assays actually they do come into the picture, they will be helpful, especially in borderline cases in combination with histopathology. Of course, cannot replace histopathology, but in combination with the histopathology, they will be helpful in borderline cases where the clinician has to make a call whether to treat the patient or not to treat the patient. So moving on to the electron microscopy, advances made in the electron microscopy in last decade. So for decades, many decades, the transmission electron microscopy has remained the mainstay in renal pathology. And however, in last few years or last decade also, I would say there have been quite a few technical advances which have been made in the detection of the backscattered electrons in the scanning electron microscopy as well, which has improved the resolution of the scanning electron microscope. See, basically, TEM usually gives very good quality of resolution, but the only thing is that these are 2D images, and 2D images, when even if you take a serial section, then 3D reconstruction is very cumbersome task for those TEM images. SEM on the other hand can give us 3D images, but because of a lot of backscattering of electrons, the resolution was always limited in SEM. So these are the technologies which have come up. They have actually detected better in detecting the backscattered electrons, and that is why they have improved the resolution in the SEM. So these newer techniques which have been can be incorporated in renal pathology. They include the 3-dimensional electron microscopy, correlative light and electron microscopy, low vacuum SEM, and scanning transmission electron microscopy. Low vacuum SEM is particularly interesting one because many of the researchers have actually used this directly on the section from the paraffin blocks. So this is something which will not require any special preparation on the tissue. Tissue can be directly sectioned from the paraffin block and stained with metal stain and undergo electron microscopy. And being a low vacuum, usually the vacuum tubes are smaller and apparatus is smaller, and there are low vacuum EM which have been manufactured and used by various researchers to show various ultrastructural alterations in renal pathology. But not as of now, they have been not in large scale in diagnosis, but definitely they are coming up. This is just a diagrammatic photograph of this electron microscopy. This is the sample here. This is the primary electron beam which is striking the sample. This is the transmitted electron beam, which actually gives the details of all the elements composition and density of the whole of the sample. And this is as you can see, this is the scanning beam, which actually gives you the surface details of the surface layer of the sample. And these are the backscattered electrons which have been generated, and these are the ones which actually will also give the details of the sample up to the depth to which the primary electron beam has penetrated in the sample. So these backscattered electrons have been the area of interest recently. So moving on to the 3D electron microscopy. Obviously, it will be superior to 2D in understanding the morphological architecture and the ultrastructural alterations, and it can easily obtain 3D images as I said, but resolution was limited. So what basically the advances which have made, they actually enable the automated serial sectioning of this tissue and imaging of this SEM by the SEM, followed by directly you can see that they can be direct 3D reconstruction. Automated 3D reconstruction is done by the software. So this is where it provides automated 3D reconstructed images which help in direct a good morphological understanding of the ultrastructural alteration. Key techniques which have been used for 3D electron microscopy, they are one is this focus ion beam SEM, one is serial block phase SEM, and the third is array tomography. So what is serial block phase SEM? In serial block phase SEM, the ultramicrosome is usually installed inside the vacuum tube of the electron microscope. Now what happens is that this ultramicrosome will do sectioning. This will be followed by the acquisition or the imaging. This will again be followed by sectioning and imaging. So this cycle will continue. And these serial sections and the serial images, then they are actually automatically 3D reconstruction of these images takes place, and it provides a 3D reconstructed image by the 3D reconstructed image of the software is provided by the software. So the researchers have shown 3D ultrastructural alteration in the podocytes and GBM in variety of mouse models of human disorders. 3D or morphological alteration of podocytes and mesangial cells in linear biopsy samples of lupus nephritis have also been shown. This is one of the images there. They have actually shown the 3D ultrastructural alteration on. This is actually EM images. This is the part of the podocyte here, and this is the mesangial matrix. And these are the here we are actually labeling the labeling of the podocyte, mesangial matrix, and mesangial cell has been done by the software. Yellow being the podocyte, this is the mesangial matrix, and GBM, and here this is the mesangial cells. And what it shows actually, this is the proper 3D reconstructed image from the software, and you can see that this is deep invagination of the podocyte into the mesangial matrix. This is the case of lupus nephritis. So in focused ion beam SEM, what actually happens is instead of the microchrome, which was used for serial sectioning of the tissue, here what is used is the focused ion beam, which actually burns the outermost or the most uppermost layer of the tissue. So again here also this will be first layer. First there will be imaging, followed by again milling, which will expose the deeper layer, again followed by imaging, and this cycle will continue. And this automatically this will be followed by 3D reconstruction of the serial image. The problem is that this gives very good resolution. The issue is that the sample size has to be limited to 20 micron. This is really very small, 20 micron. The sample damage can also take place due to the ion beam current and loss of sample by the milling. And of course, the cost of equipment is a major limiting factor. And thirdly, the technique which has been used is array tomography, where you do serial sectioning in the conventional microtome only, but they are actually taken on a specific slide with a magnetic tape. Serial sections are taken on slide with a magnetic tape, and then they are actually analyzed in the images are analyzed in the software, and 3D reconstruction again will be automatic. So the advantage here is that it can be used for larger tissues, because here the microtome, ultra microtome which is used is our conventional ultra microtome which is used for electron microscopy section, and the sections can be preserved for subsequent electron staining methods. Moving on to the low vacuum SEM, as you said, with low vacuum SEM, the apparatus is small and very low cost and easy to use. Low vacuum SEM has been provided by EM companies, and they have been used in research as of now, and demonstrated the application of low vacuum SEM directly to the paraffin embedded renal tissue biopsy without special preparation, and they have given good quality images for that as well. And finally, this is the correlative light and electron microscopy, wherein it enables the visualization of the ultrastructural changes specifically in the area of the interest, where the light microscopy image will be usually taken from either IFC or immunofluorescence image. Then the same area is actually same section is stained with after metal staining and observed for TEM or SEM, and then both these images are actually correlated by the software to see what are the ultrastructural changes in the area of the image. Moving on to the gene expression based assays in the transplant. So these assays they provide measure of gene expression profiling in the biopsy sample and give the risk assessment for the rejection and injury in the transplant. They measure the mRNA transcript level in the biopsy sample, and which is actually then fed into the algorithm to give the result. They compare the features of the biopsy to a standard specific reference set, and they can be used in combination with histopathology. This is just the glimpse of the report which they give, demographic data. Then you have the details of the genetic changes, gene expression changes which are there in the particular tissue sample, and then you have the graphical representation of the in this region, in which region the patient is to be lying. Whether it is in high rejection region or is in no rejection given. However, these must be taken with a pinch of salt when these are the assays which still I feel that require larger validation and thorough clinical validation. It is one of the studies where actually they have seen where the discrepancy was. So they have actually studied 15 kidney transplant recipients in this case, and out of 15, 33, one third was the one without any discrepancy, and one third, almost 18, they had discrepant findings. Among the discrepant findings, the 15 was the one where there was rejection by histology but no rejection by this MMDA. In the 3-1 where there was no rejection by histology but they were shown as rejection by MMDA. These 3-1 actually, one of them was AIN, and two of them were actually DKD, which actually was shown as rejection, given as rejection by the MMDA. Now, amongst the 15 cases, they were actually shown as rejection by histology, but no rejection by MMDA. 6 were the ones in which the combined endpoint was achieved. The combined endpoint here in this case was that either the patient responded to the therapy, or the patient had a loss of graft, or the subsequent biopsy rejection was proved clearly. In 6 of them, most of them eventually turned out to be rejection on the hospital biopsy. One of them, which was ABMR, it turned out to be ABMR on follow-up biopsy as well. This borderline rejections also had improvement after treatment, and 2 cases with PCMR, they actually improved after treatment, and 1 actually showed ongoing PCMR on follow-up biopsy. Where the other cases where the combined endpoint was not achieved, 4 actually still turned out to be ABMR, but the 5 cases with borderline rejection, they were the ones in which because no treatment was given, so the common endpoint at that time was not achieved. But I would still say that there is discrepant finding in almost 1/3 of the cases. There is another study here. Even here we can see that almost in 37% of the cases there is discrepancy. In 19%, there is clear discrepancy. Clear means that one platform is saying rejection and other is saying no rejection. The other, in around 5%, is mixed discrepancy, where one is saying that it's combined rejection, other is saying it's only one type of rejection only. And around 14%, there was boundary. These are the borderline cases. One is saying that it's borderline rejection, the other is saying this is no rejection. But definitely, this will require more thorough clinical validation. Even though I think this assay has been approved by FDA and it is used, in US, in various areas in US and Europe, it has been used. They actually take the biopsy samples from all the centers and they send it to the central lab in Canada where they actually do this. So moving on to the final part, this is the artificial intelligence in renal pathology. Artificial intelligence still is in early stages of development in the field of nephropathology when compared to other fields of pathology, especially oncopathology, where it has come up in a big way. The reasons could be that one of these is the complex architecture of nephron, which is fine, but the main reason which I feel is the difficulty in integrating the clinical data, lab data, light microscopy, immunofluorescence, and EM findings, and then actually giving a complete picture in a biopsy report. This actually requires cognitive ability, which as of now, the current algorithms, they're not able to give a wholesome picture. Yeah, definitely they are very good at doing the well-defined task. For example, if you have to score a fibrosis in a biopsy, this will do. The AI will, this algorithm will do very well. Counting the number of glomeruli, these algorithms will do very well. Identifying the proliferative glomeruli, they will do well, but giving a complete picture based on all the data, then use is limited. So it is mainly used for tedious but well-defined tasks, as I said, and especially in transplant pathology, where you have to score the fibrosis, you have to score the tubulitis, there this can be used. Another reason could be that the large data set with clinical metadata required to train complex neural networks in this AI. This is still lacking. This is just this simplified photograph how they actually develop this this prediction models. And this is actually the first step usually is data collection. And after data collection, they actually do the images whole slide scanning is done, and the whole slide scanned images actually are then fed to the complex neural network. And similarly, the input from the pathologists they are also fed for this images, and then based on this clinical findings as well as the other data, they give a complete picture. But still, this is just a simplified workflow. A good robust platform which actually gives a complete wholesome picture is still lacking for renal pathology. This is just various types of neural networks. This is earlier first generation, which was simple one, where there was no hidden layer between the input and the output. And now, as we can see, that this is the complex neural network. And this is just beyond my understanding as well. A lot of layers between the input. Input usually is your morphological whole slide scan images and the input from the expert pathologist, and output is the final diagnosis. It has been used, as I said, in certain well-defined tasks like detection and segmentation of renal structures, as I said, for sclerotic glomeruli, and it has shown good degree of accuracy for at least identification of such structures. For scoring of interstitial fibrosis, as well as for lupus nephritis classification, they have glomerular classification they have actually used, but not for a complete incomplete wholesome report. So in various disorders, they have used for specific well-defined tasks. So when you see to fully exploit the potential of artificial intelligence in nephropathology, very close collaboration between nephropathologists as well as AI experts is required, wherein each of these groups they actually understand the complexities as well as the limitations of the other field. For example, a nepropathologist has to understand that not everything can be represented by AI-based model, so they have to understand the limitations. And similarly, the AI experts will have to understand that they have to understand the complexities of the renal pathology, wherein you have to incorporate all these findings to give a complete picture. And obviously, they will require a well-curated multi-centric data set and training of the involved person in the clinician. So in the end, to summarize, the paraffin immunofluorescence as I said is a valuable technique in renal pathology and can be used in specific situations, particularly C3 as well as in glomerulonephritis, where we see discrepancy in the light and immunofluorescence findings or immunofluorescence and in EM findings as well. LMD and mass spectrometry based proteomics can play an important role in diagnosis of non-AL and non-AA amyloid as well as in identification of newer antigens in membranous. Large-scale quantitative proteomic profiles can help in characterization of the glomerular disorders as well as determining the pathogenic mechanism and may open the avenue for novel therapies. Recent advances in electron microscopy can enable direct ultrastructural examination from paraffin embedded tissue as well, which might be upcoming. So paraffin immunofluorescence and paraffin EM, these are the ones which might. Paraffin immunofluorescence has already come up in a big way. But paraffin EM, you might see that paraffin EM is something which is because not many centers they have the facilities for ultramicrotomy and everything. So this is a good technique. And finally, the tissue-based molecular assays or the gene expression assays like MMDX, they require rigorous clinical validation with large multicentric studies. Unique complexities of nephropathology makes it excellent testing ground for various AI approaches and can generate and can create generalizable models for other research fields. Thank you. So these were my references.
Thank you, Dr. Amit, for your
So one of them is your clearly when you have GBM abnormalities. For example, thin basement membrane disease or Alport syndrome. These are the ones. So clinically, you will see the cases which will have hematuria, and not much of proteinuria with them. And secondly, uh, they will be negative on immunity. These are the cases where still you will look for directly sending electron microscopy, because these are the things which can be directly performed on electron microscopy only and not on light and microscopy.
Can have significant artifact after being frozen in therapy, right? We have seen them. So if you want to send, then we will directly send them to
So you're talking about artifacts now? Yeah,
yes,
I agree that from rather than paraffin block, as of now with current technology, it will be, it should ideally it look at the electron microscopy.
As a clinician, if there are, I am doing biopsy for anephrotic indication, then certainly I will look for the electron microscope, because I am not expecting major large changes on the light microscopy or IF. There I will certainly ask for a EM option, because or headed familiar cases where we are looking for something which is on electron microscope not available on IF and light microscopy. And one more question. Is there any advances, because all this needs better tissue for whether you do IF or light microscopy or EM, and it is always disheartening to sometimes see inadequate biopsies or tissue not found on EM. So are we doing anything on that front to make sure that as a pathologist you get an adequate sample by doing advancement at a bedside or at a biopsy site? Because it's always better to have good tissue for all these processes.
I'm not getting it. Advancement at bedside means
When we do biopsy,
yeah, we do look for adequacy definitely.
Yeah.
At that time itself, we allocate the tissue for electron microscopy.
all we not have on the
Yeah.
Are you training the people who are sending biopsy to do the adequacy?
Yeah.
Same question to ma'am also, because ma'am
Yeah.
also gets sort of.
Yeah. Either a good quality magnifying glass or, as madam said,
Ma'am showed that in her online classes one time. Actual iPhone picture, and then she zoomed in and we could see the.
all going to be totally
one more thing I want to add for our clinician friends, that is to prevent hemorrhage post biopsy complication. They are going for a higher gauge needle, that is, so we are getting thin and thin core of biopsy. So preferably, if possible, just use our lower gauge needle 14 or 16, just so that we get a
6 years ago now standard.
so, and also make sure that your needle are fast, because many times you are overusing those needles and you are getting a fragment of biopsy, which is not
we do
not
get
from our
actually-
centers, but
we do get 18 gauge biopsies actually from outside, and that is where actually we struggle with the adequacy. And of course, as I said, that
comparable between 16 and 18.
this is where actually, as I said, that there your not just light microscopic synthesis, even for immunohistochemistry section, there again we find the case. To be
one. I mean, in young kids, you don't have to be the 18 days. When winters, obviously, you go in 18 days. But now, younger transplant kids protein is what you have to do in 18 days. And after all of this, have to happen to what you provide in terms of cold.
pediatric no issue.
Okay, I am not in this. Sorry. So, secondly, why we said non-nephrotic cases. Do understand that alcohol is now the biggest mimic of nephrotic syndrome in adults as well as children. So, in that context, I don't think it's going anywhere that we can say. If you have microscopic hematuria, do you want to yes.
Are we doing the IF therapy?
IF cannot replace.
IF cannot be replaced with therapy. Therapy in IF can be a good companion to routine immunotherapy, but certainly do not replace therapy.